In case of low frequency circuits, to find out voltages and currents, we apply KCL and KVL. After that, we get the second order differential equations, and by solving those second order differential equations, we find out the corresponding voltages and currents. So in the same manner, in case of electromagnetic wave propagation, the flow of energy, it is not in the form of voltages or currents, whereas it is in the form of electric fields and magnetic fields. So usually to find out electric fields and magnetic fields in the same manner, we should have the differential equations in terms of electric fields and magnetic fields. So these type of equations are called as wave equations for electromagnetic waves. So let us proceed to find out what exactly are these wave equations. These are very important for finding out solutions when the wave is propagating in free space or in a transmission lines or in a waveguides or in fiber optic cables. So let us proceed to find out these equations called as the wave equations. So these wave equations can be obtained by relating the space and time variations of the electric and magnetic fields. So as we have seen, the Maxwell's equations give us how the electric fields and magnetic fields, they are related to each other, because the electromagnetic wave consists of electric fields as well as magnetic fields. So the Maxwell's equations give us the relationships between electric fields and magnetic fields. So by solving this Maxwell's equations, we can get the corresponding differential equations for E or H, which we call them as the wave equations. So before we proceed, we make certain assumptions. So the assumption number 1 is the electric and magnetic fields exist in linear, homogeneous and isotropic medium. So we assume the medium is linear, homogeneous and isotropic with reference to the parameters epsilon, mu and sigma, that is permittivity, permeability and conductivity. The other assumption is the medium is source free. So that means there are no sources in the medium. In other words, it is a charge free medium. Third assumption, it obeys Ohm's law. So in case of electromagnetics, the Ohm's law is J equal to sigma B, where J it is the current density, B is the magnetic flux density. So with these assumptions, let us proceed to find out these wave equations. So we start with the Maxwell's equations, what we have derived earlier. Now one of the Maxwell equation was curl of E is equal to minus dB by dt, that is rate of change of magnetic flux density. So in this equation, if we substitute B equal to mu H, then this equation we write it as equation number 1, that is curl of E equal to minus mu dH by dt. One more equation we have seen earlier is curl of H, we defined in the form of current density. So right hand side it is the current density, and we have seen there are two current densities, the conduction current density Jc and the displacement current density Jd. Now the conduction current density is sigma E, sigma is the conductivity, so this is the conduction current density, and the displacement current density we have seen earlier, rate of change of electric flux density, that is dD by dt. By substituting D equal to epsilon E here, we can write the displacement current density as epsilon dE by dt. So this is equation number 2. We have seen earlier, as the magnetic field lines, they always exist in the form of loops, or in other words, the magnetic monopoles do not exist. So based on that, we have written earlier that divergence of B is equal to 0. Now since B is equal to mu H, from this we can say divergence of H is equal to 0. So this is our equation number 3. We also proved earlier that in case of electric fields, the divergence of D is equal to 0. Or substituting D equal to epsilon E, we can say divergence of E is equal to 0. So these are our 4 equations from which we find out the corresponding wave equations. So if you see these 4 equations, so these equations give us the relationship between electric fields and magnetic fields. So which is similar to the relation between voltage and current when you apply KCL, KVL for the low frequency circuit. So as we have seen, these 4 equations give us the relationships between electric fields and magnetic fields. So by solving these equations, for example, from equation 1, if we eliminate H, then we will get equation only in terms of E. So this we will get a second order differential equation in terms of E. Whereas by solving these equations 1 and 2, if I eliminate E, then we will get the equations in the form of H only. So we will get this corresponding equations, one equation, second order equation, which is function of only electric field, another second order equation which is function of only H. So by solving those equations, we can get the solution for the corresponding electric field and magnetic fields. So this is what is actually wave equations. So starting from these 4 equations, let us move ahead to find out the expressions for these wave equations. So let us eliminate H from equation 1 to find out E. So to begin with, to eliminate H from equation 1, we take curl of both sides of equation 1. So let us rewrite equation number 1 by taking curl of both sides. So this is curl of E is equal to minus mu curl of dH by dt. Now in this bracket, on the right hand side of equation number 5, the del operator and the derivative operator, this can be interchanged. So rewriting this as minus mu d dt curl of H. So let us continue with the equation. Curl of E is equal to minus mu d dt del cross H. Now let us substitute this del cross H from equation number 2. So from equation number 2, we have seen del cross H is nothing but the current density, what we have seen earlier. So that is conduction current density Jc plus displacement current density Jd. So this is conduction current density and this is the displacement current density. We have substituted from equation number 2 here on the right hand side of equation 6. So simplifying this, right hand side I get minus mu sigma d by dt minus mu epsilon. Now this is second order derivative d2e by dt square. Now by making use of one of the standard vector identity, that is curl of E is equal to del dot E minus del square E. So we will make use of this vector identity, and the left hand side of equation 7 we will replace by this term. Now from equation number 3 we know that del dot E is equal to 0. So substituting del dot E is equal to 0 here, equation 8 simplifies to curl of E is equal to minus del square E. So we rewrite the equation 7 by replacing left hand side by minus del square E. So left hand side of equation 7 becomes minus del square E. So substituting this, the equation becomes minus del square E equal to minus mu sigma d by dt minus mu epsilon d2 E by dt square. So removing the negative sign on both sides, now we get this equation del square E equal to mu sigma d by dt plus mu epsilon second order derivative of E. So this is our one of the wave equation for electric field E. So this equation number 10, on both sides we have now electric field. So this is similar to a second order differential equation for voltage. Now this particular equation, it is for electric field. So this is the wave equation for electric field E. Now to get the wave equation for electric flux density D, we multiply both sides of this equation by epsilon. So we write it as del square epsilon E. Now substituting epsilon E equal to D, we get the wave equation for D. So this is the equation number 11, is the wave equation for electric flux density D in uniform medium. So we got the wave equations for E and D. So in the same manner, let us find out the wave equations for H and B. We'll have to eliminate E from the first 4 equations, what we have seen earlier. So taking curl of H of both sides of equation 2. So equation 2, what we have seen earlier, it was del cross H equal to the conduction current density plus displacement current density. So this is the conduction current density and this is the displacement current density, that is del cross H. Now taking, so this is conduction current density, that is sigma E. This is conduction current density sigma E plus the displacement current density d by dt, that is the flux density. Now taking curl of both sides, so this becomes curl of H equal to curl of sigma E and curl of dd by dt. So we substitute here d equal to epsilon E. So this is equation 12. Now as we did earlier, we can interchange the order of the operators, del operator and the derivative operator, rewriting this as epsilon d dt del cross E. Now in this equation number 13, we will substitute del cross E. So substituting del cross E equal to minus mu dH by dt in these equations, here we get this as curl of H is equal to sigma minus mu dH by dt plus epsilon minus mu dH by dt. Now simplifying this, this is minus mu sigma dH by dt minus mu epsilon d2 H by dt square. Now the left hand side This is a standard vector identity as we have seen earlier. Del cross H, it is a vector identity which is equal to del dot H minus del square H. And as we have seen from equation number 4, this del dot H is equal to 0. If I substitute del dot H equal to 0, this reduces to del cross H equal to minus del square H. So in the equation number 14, for left hand side we substitute as minus del square H. So substituting the left hand side in equation 14 as minus del square H, now we get this equation which is in the form of H only. Now rearranging this, adjusting the negative sign of both sides, we get del square H equal to mu sigma dH by dt plus mu epsilon d2h by dt square. So this is the wave equation for magnetic field H. Now by substituting B equal to mu H, we will get the equation for B, magnetic flux density. So multiplying by mu on both sides, so this becomes mu H. Now substituting mu H equal to B, we get the wave equation for B. So now we got the wave equations for the magnetic flux density B and magnetic field intensity H. So we got all the 4 wave equations. Now if I combine, we can represent all the 4 equations in terms of a matrix like this. So this is the general wave equation which will be useful for solving problems to find out the magnetic flux density, magnetic field intensity, electric field intensity, all these 4 terms. In case of transmission lines or waveguides or uniform plane wave propagations, these are the applications where these wave equations are useful for finding out the solutions.